This is the first part of our Unit 11 notes. In Unit 11, we're going to be studying light behavior. In the following unit, in Unit 12, we'll be studying optics. So in this one, we're first going to talk about different behaviors that light has. This includes reflection, refraction, interference, and diffraction. Those are all wave behaviors of light, so that's what we're going to focus on in this section. All waves have these properties, but here we're going to apply it mostly to light, although we will look at a few other things as well. The first thing to think about with light is, what is light? Imagine an alien came from space, that's my beautiful little image there, and he came to Earth and he had no eyes. So he asks you, I've heard about this thing called light, please explain it to me. How would you explain light to someone who has never seen? It's kind of complicated. It's different than other things that we experience. And actually this question of what is light is something that scientists struggled with for a long, long time. And they finally came upon a theory that said that light is a wave of photons that has an electric part and a magnetic part. And the photons then are packets of energy. So there are some parts of light that act as a wave and some parts that act as a particle, some behaviors. So they say that light has a dual wave particle nature to light. So, and that has some interesting consequences, and we'll look at some of those things in this unit. A few things that we should know about light is that everything that's an electromagnetic wave is light. That means radio waves, gamma rays, all those things you've surely studied before on the electromagnetic spectrum, those are all light, although humans can only see a very narrow band of light. And you should know this range. It's a good factoid to have in the back of your head. Between 400 and 700 nanometers, where a nanometer is 1 × 10 to the negative 9th meters. You see nanometers used a lot in this chapter, and that's just because since that is the order of magnitude of light that we can see, of visible light, you will see that used a lot. So that's a prefix if you didn't already know that you should learn. An interesting thing about light as compared to sound that we just studied is light does not have to have a medium through which to travel. And that's something that kind of threw off scientists for a long time, because they said, well, light can't possibly be a wave because light goes through space, and space is empty, so there's no medium for it to travel. So that is something that caused them a lot of thought, and something they kind of had to figure out. Most of what we're going to look at in this lesson is how to diagram light waves. We won't be doing any math here. It's all sketches. Whenever you do sketches for light waves, you must use a ruler. If you give me a wavy line that's supposed to be a light diagram, I'll be very unhappy with that. It doesn't even have to be a ruler. It just has to be straight. You can use, your cell phone or, a book or whatever you happen to have. So as we diagram light waves, the first thing that you need to have is the ray itself. Sometimes these rays have labels, and we'll look at that in reflection or refraction, what they're called. But you have the ray, and the ray has an arrowhead indicating the direction that it's moving. Something that is a little bit different is they also have wave fronts. Wave fronts, think about them as wave crests. So if you were looking over, if you were looking above from like the ocean and you were watching waves come in, you would see crest, crest, crest as the waves come into the shore. That's what you're looking at here. So the distance between the wave fronts are an indication of the wavelength. So the closer those are together, the smaller the wavelength, and vice versa. With those also, this almost seems like a little bit redundant, but sometimes you're given a problem where you don't have the ray and they give you this instead. So they have these things called velocity chevrons. A chevron kind of like an army guy would have on his shoulder patch to give his rank. It's just the V looking thing. And the chevrons are basically like having an arrow with just the pointy part of the arrow. So it tells you which way the ray is going. So those are all the parts of a ray diagram. So now the first thing we'll talk about here is reflection, and I'm going to sketch those other wave parts onto this diagram. But first, let's talk about what these things are. Whenever you have reflection, you have something that is going to, a light ray is going to come in, and then this horizontal bar here then would be the mirror, and it's going to bounce off and reflect the other direction. So that's our typical reflection. When we do this, we need to talk about a few things. We need to talk about certain angles, and those angles are always measured from the normal. The normal, if you remember when we studied forces, the normal was always perpendicular. It's a math word. Normal means perpendicular. So the first thing we always do when we sketch a ray diagram, after you have the rays, is you sketch the normal, and the normal is perpendicular to the mirror here. And it's usually a dot dotted line, just so you know it's not a real ray and you don't get that confused. But the angles are measured to the normal, and that's very important. When we problem solve, occasionally they will give you the outer angle, and they're just trying to trick you. It's really not all that tricky if you understand the idea, but they'll give you this angle and you'll have to do 90 minus that to find the angle to the normal. So that's important to know. So we have the incident, meaning incoming, and the reflected, meaning outgoing. So whenever you have reflection, what you're doing is you're just changing the direction of the light, but the wave is going to stay in the same medium. That's going to be the opposite in refraction. So here's our terms. So incident means incoming, reflected means outgoing, and then the normal I just explained is drawn perpendicular to that barrier. And when they say the barrier on reflection, they're usually talking about a mirror if nothing goes into the other barrier, it goes through the barrier at all. And we'll see some where they go through and some where they don't. So that brings us to the law of reflection. You'll like this law because it's easy. The law of the angle of incidence is always going to equal the angle of reflection. So whatever angle a ray comes in at to a mirror, it will reflect out at the same angle. I don't think that one's too confusing. So I went ahead and sketched on my wavefronts onto this. So my wavefronts come on, and see what I did here? I had the wavefront hit the mirror and bounce back. By the way, wavefronts are qualitative, meaning you don't have a particular number that you have to draw, and they don't have to be a certain length. So as long as you follow the basic rules, you have to keep going all the way to the mirror, but you need to come all the way in, come all the way out. Doesn't matter how long they are. They should be equal spacing because the wavelength does not change. And there I put the velocity chevrons on the top. Okay, it does not matter which side of the ray the chevrons go on. They can be sketched on either side. Okay, so now refraction. Refraction has some, well, I wouldn't say it's similar to reflection, but it is as light travels, then instead of staying in one medium, it's going to go through to the other medium. So a classic example is a pencil. So if you take a pencil and you put it in water, you'll see that the pencil looks like it's bent. You've experienced, I'm sure, the same thing. If you take your arm and stick it in, the pool, it'll look like your arm is bent when you know it's not. It's just the way the light bends when it goes into the water. So there are some rules that we're going to learn for refraction. The first thing to know is that when you go from fast to slow, the light will bend towards the normal. We'll do this mathematically later, so for now just qualitatively. If you go from a slow medium to a faster medium, the light will bend away. And an easy way to remember that is Fran. Fran says faster refracts away from normal. That means into faster. So if you start in slow and you go into faster, it's always going to refract away from the normal. And when we look at different mediums that we're talking about, the more dense the medium, the slower the velocity. So the fastest medium that light can go through is going to be a vacuum, so outer space. So the slower the medium, the more dense it is, or the more dense it is, the slower it is. Okay, here's why refraction happens. What I always like to do when I have the board with me is I like to take a little car and I put the car here on the fast side. And if you take the car and you drive it, and say this is like dry land, and you hit water, what's going to happen as soon as this wheel on the right hits the water is it's going to slow down while the wheel on the left is still going the same speed. So what happens? The car is going to turn a little bit and bend. That's exactly what happens with refraction. So you have part of the light in the old material, part in the new, and that's what causes the light to bend as it goes from one material to another. So here's how diagrams work with refraction. So we have our incident ray here, and it's going to go from fast to slow. So the solid line is my change in medium, and the dotted line I've already sketched the normal in. The normal is always perpendicular to the barrier, not perpendicular to the ray. Okay, big difference. So perpendicular to the barrier. So as I bend it, I'm going into slow. So this is not Fran. I'm going into slow, so I'm going to bend towards the normal. Then I went ahead and put on my wavefronts. Notice the wavefronts are further apart in the fast medium and slow and closer together in the slow. So imagine you're driving really fast and you throw a penny out of your car every second. They're going to be further apart when you're going fast, and if you do the same thing, throw the penny out of your car every second, and when you're going slow, those pennies will be closer together. So that's why they're further apart in the fast medium. So there's my chevrons. That only tells me what direction they're going. And then I want to label my angle. So I have the angle of incident to the normal and my angle of refraction to the normal on the other side. So that's a classic refraction diagram. So in real life, most of the time you have both reflection and refraction happening at the same time. So here's a diagram when you have both of them. So this is slow and fast, and I did medium changes at different angles, so you don't always think of it the same way. So I've got this one kind of at an angle. And here's my incident ray. Okay, so my incident ray is the red ray. Don't be confused by the black ray, that black arrow that's pointing to the incident ray. That seems a little redundant. But I have my red arrow is my ray pointing into that's going to hit the barrier, and part of it will be reflected and part of it will be refracted. So first thing I always do is draw my normal. So I went ahead and did my normal, and then my angle of incidence is always measured to the normal. So there's my reflected ray. That should be at the same angle. So the angle of incidence and the angle of reflection should be the same size. So there is my refracted ray. In this case, I'm going fast to slow, so it's going to bend towards the normal. So this is my basic diagram, and now I'm going to add the, you could call it the confusing stuff if you want. So here comes all of my wavefronts. In the fast medium, they're going to be spaced out a fair amount and closer together in the slow medium. So that set should be the same spacing as the incident, since the reflected is the same speed of medium, so those are supposed to be the same. And then as I go into the slow, those are the ones that are closer together. So that's my entire reflection and refraction diagram. And I believe I'm going to have to do a separate video on the very last, well, maybe let's see if I can squeeze it in and see if YouTube likes me. So we've talked about V equals F lambda a lot, and in the last few chapters, let's see if we can apply it to light. When we talk about light, the first thing you should know is the speed of light in a vacuum is a constant. It's the variable c, and it's 3 times 10 to the 8th meters per second. Always, 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 always. But when you take the light and you put it in different mediums, you will have a different speed. The interesting thing is that the frequency of the light does not change, and the reason for this, we won't go into detail with this here, but the reason for that is that the energy does not change when you change mediums. So if the energy does not change, energy and frequency are directly related. You may have seen that little equation there. We won't use it in class, in this class, but you may have seen it in others. Because the energy doesn't change, the frequency doesn't either. But because of that, if the frequency is the same, that tells you that the speed and the wavelengths are the ones doing the changing. So because V equals F lambda, if you look at the equation, if V increases, then lambda is going to increase as well. So those are directly related to each other. So that is where I'm going to stop, and we'll see if YouTube will let me have a video this long.